Hi, okay, so welcome to Nonlinear PDE's course. So this is a course I developed over many years. I've taught it at the University of Auckland. I've taught it on the MC Summer School, and I've taught it on the Access Grid a few times, as well as teaching it at Newcastle Uni. So the course is based on this WikiWaves website here, and there's 12 topics. Each of these is a lecture, basically. So we're going to start with this first one, method of characteristics for linear equations. Then we go to lecture 2 will be traffic waves, blah, blah, blah. Okay? So I probably won't record each lecture. I'll record each lecture in a few blocks, a few parts, just depending how we go. Okay? I don't want to make them too long. And this first lecture won't be super long. So the wiki thing, I just want to quickly show you. So it's nonlinear shallow water waves. Easily editable. It's not the perfect format. It's maybe easier to see as a text, and if you print it, it doesn't print as beautifully as the document, say in LaTeX. But you've got some things here. There's a picture of the solution. Here's a picture of the shocks, and if you click on this picture, it'll take you to the code that was used to create it. Alright, in MATLAB. There's a little bit of MATLAB programming in this course. So one of the things I really want to emphasize in this course is drawing pictures, solving it, calculating a picture, a numerical answer of it, and visualizing it. So there's no point being able to solve a PDE, in my opinion, if you can't actually draw a picture of it. I'm not interested in you telling me that a solution exists. I want you to find the solution for me, and I don't want a formula for the solution. I want you to turn that formula and compute it. Alright, so you've got a little bit of stuff here. Okay, and it goes on over there. These are the notes, and then there's some pictures here. You'll understand it. Here's a picture of a piston pushing forward into water and explaining to you how you get these shocks forming. There's a few YouTube videos here. This is my favourite one here of them all. So you know that I found that I've embedded. Okay, so you've got the idea here that you're going to go through these notes. There's assignments and things for the course, and that get you to do some work through the different problems and understand them, and allow you to do some computation. So there's a few things that unify this course, and we'll talk about that in a second. Let's just get started a little bit. So, whoops, here we go. Okay, so let's just go here. So the course is called Nonlinear PDEs. PDE meaning partial differential equation. So, I'm going to use this little pad here to write some of our stuff down as though it's a whiteboard. Okay, so we know what partial differential equations are, and they're just super important. If you look at here, you look up something like the top most important equations in the world or something like that, you'll find that so many of them are PDE. Okay, so I just typed in here most important equations. There's 17 equations that change the world, Business Insider, most famous equations. Let's have a quick look at them quickly. Pythagoras' theorem, complex numbers, logarithms, calculus, law of gravity. These are Maxwell's equations. So these is the partial differential equation here. Maxwell's equations are PDE. General relativity is really a PDE as well. It's not written in an obvious form. Okay, so maybe that's not such a great idea here, proving stuff, proving me wrong. Keep me posted. No. Let's try this thing here, 17 equations that change the world. What have they got here? Pythagoras' theorem. Wow, there's a lot of ads all over the internet, isn't there? See what's going on here, man. This is stupid. Logarithms, we're around that. Derivatives, calculus, gravity, which is a differential equation, really. What is formula? Normal distribution. There we go, wave equation, there's a partial differential equation. Fourier transform, there's another Navier-Stokes equation, another partial differential equation. Maxwell's equations, partial differential equations, model thermodynamics, area of relativity, Schrodinger's equation, another partial differential equation, Shannon information theory, logistic model, it's getting very serious, Black-Scholes model, another partial differential equation. Okay, so you see there's loads of them, half of them are partial PDE. So we're not making it up when we say PDEs are super important. I wanted to show you that. Okay, so note the graph theory equations or whatever they're just not in there, and no one thinks they're that important. So partial differential equations are super important. And when we're going to have nonlinear partial differential equations at the topic of this course. So we're assuming that you know about, we know linear partial differential equations, but it doesn't actually matter too much if you've forgotten that. So we just wanted to talk quickly about linear before we get started in a few things. So we've got one of the first thing is this. Here's PDEs. This makes sense. And here's linear PDEs. They're a subset, aren't they? Of them. Now, sorry, what am I doing? These are the linear ones. Okay, so they're a subset. So what we've got here is everything else, and you can't really define something by what it isn't. So when we say nonlinear PDEs, this is just this set is very large and very broad. So really what we're going to do here is we're going to actually, what the topic has to be is some other ones out here that we can solve, that have some properties that allow us to solve. So we can't cover all nonlinear PDEs by definition, right? So it's some, right, that we're going to cover. Okay, I mean, you can't define something by what it isn't. So nonlinear PDEs is defining something by what it isn't linear. But it does make a lot of sense because the techniques you use for linear PDEs are quite special, and we have to throw those out. And the most important one is superposition. So that's the most important property of linear PDEs. So if you have two solutions, then you can add them together and get another solution, or you can multiply them by a constant. And we've lost that with nonlinear PDE. So we have to use quite different techniques. So in fact, if you've forgotten everything about linear PDEs, it won't be super important because the course doesn't very strongly rely on linear PDEs. There's not a strong connection. These ones out here have different techniques. We'll see a little bit of a connection with them. Okay, so PDEs are important, nonlinear PDEs are important. And we're going to learn how to solve some of them, okay? When we say solve, we're going to have three different things here, right? We're going to have the analytic, we're going to solve these equations, right? So we're going to have one is going to be an analytic solution, which is a solution which really means a formula. And two, we're going to have numerical solutions. And then all of these we're going to add together, and we're going to make sure that we can draw. Okay, even the analytic solutions, we're going to draw a picture. Everything is a picture. We can't draw a picture of it. We can't solve it on a computer and find a number out of it. What's the use of that analytic formula? It's a beautiful thing to write down, but in the end, it's got to be used to calculate something. The answer is the number that you can calculate. It's no good having a formula for something that you can't actually work out, like numbers in. So we're going to draw pictures using either of these methods. And we're going to use numerical solution. In this course, we're going to focus on one numerical technique, and we're going to keep coming back to it. So what you're going to learn about is you're going to learn about three different kinds of nonlinear PDEs effectively. Right? So the course is going to have three types of, so three basic types of nonlinear PDE, right? Oops, I keep writing D instead of E instead of D. So there's three types of nonlinear PDEs, and we're going to have one numerical method that we're going to use. It's a very useful numerical method. Okay, so you're going to learn in this course, you're going to learn about this numerical method, and it's a split-step spectral method. uses it's highly connected with the fast Fourier transform. It's very easy to program this method. It's very accurate. It's a great method to use, and it can solve lots and lots of different equations. So we're going to understand this method, and as we go through the course, we'll come back to this method and understand it in more detail through the course. So you'll kind of learn it in stages. We'll keep revisiting it and learning more about it.